Hello. Nearly there. We're absolutely counting down at this stage. So, today I'll talk about sedimentary hydrothermal environments. So, this will be the last lecture on ore deposits specifically. Next week we'll talk about environmental consequences to round out the trimester. So, we're most of the way there. The light is at the end of the tunnel, I promise. So stick with it. So today I'll talk a bit about SEDEX, so sedimentary exhalative deposits, redox, sedimentary deposits like red bed. So these are also related to stratiform sedimentary copper deposits. Also talk about carbonate hosted base metals. So these, you might also see these referred to as Mississippi Valley type deposits. And we'll also talk about uranium deposits, which link to redox states, as we've seen is very important for many mineralizing systems. So firstly, SEDEX, so sedimentary exhalative. There is a broad continuum between SEDEX and VMS deposits, so we can think about our black smokers or venting systems where the hot fluids have moved through sedimentary systems, potentially meteoroic, and they've dissolved lots of base metals from those sediments, particularly lead, zinc, silver, copper, and then they move through these vent structures, and then they interact with colder water, and then they cool and precipitate out metals or exhale metals, and they form sedimentary layers that are progressively zoned. So that's what they broadly are. So you can see how they link to the vent or the VMS, but they're a distinct style of exhaling these precious metals. So the metals are carried by chlorine complexes. The fluids are predominantly basinal in derivation, so they're low temperature, neutral in pH, and saline. And they're heated as the basinal brines move through the sedimentary rocks and leach metals out. And the fluids then move back through a structurally controlled vent, usually extensional faults or something like that, and then they they vent into that fluid, and the sulfides are precipitated as it cools and mixes with the dilute colder waters. And this produces these aprons of sulfides, and they're commonly laminated, conformable to bedding because they're largely syngenetic in origin. So the fluids, as mentioned, are generally low temperature, certainly less than 200 degrees, neutral pH. The alteration is usually quite weak because of low temperatures, but it involves a bit of silicification, dolomitization, and maybe some tourmalization. And the metal sulfides, things like pyrrhotite, sphalerite, galena, pyrite, may replace early form sedimentary pyrite as the primary source of sulfur, formed through biogenic reduction of sulfate sediments. So the sulfur is originally sourced from the fluids that have deposited the sediments, and then biogenic activity reduces that to sulfates, and then these fluids incorporate that sulfur and transport it, which then binds with the metal. So the host rocks are usually these fine-grained plastic rocks, siltstones, mudstones of sort of rift basin. Here's a good example of a SEDEX massive sulfide. So we have spectacular layers of galena, pyrite, and sphalerite. So lead sulfide, iron sulfide, and zinc sulfide. And in this case, it's deformed. Potentially, some of this might be related to soft sediment deformation or just later compression or other forms of tectonic deformation. So here's a generalized cross-section. We have our sedimentary sequence. We have flow of water to a deeper heat source. We're leaching out metals, sulfur and silica. We move through feeder zones or conduits that are related to the faults. We form these sort of broad vent structures where we might get iron copper sulfides. We get a bit of zoning. The fluid vents interacts with the water body and then precipitates out stratiform sulfides as lead, zinc, iron. We might also get things like barite and peripheral halides where we get iron, magnesium and things like that, which are more soluble at lower temperatures and precipitate further from the source. And the alteration is very narrow and related to these conduit fault zones. So some type examples would be things like potentially Broken Hill, although it's debated as we discussed earlier on. Mount Isa is also broadly debated. Some people think it's actually epigenetic. There's a replacement on these sort of systems, so we have to take care. Here's just an older idealized cross-section. Here's our vent related to a fault. We might get some brecciation in places. We have our primary ore bodies and we get aspects of brecciation, potentially with some stratabound zones of alteration. It would have vented out and we form these prominent stratiform exhalative horizons into the top part of the sequence, and we get a broad zonation. Okay, so that's SEDEX, variation on a theme. Next we'll look at redox deposits. Okay, so these relate to elements that are highly dependent on the redox state. So reduction and oxidation become vital, and this is going to be applicable to elements that have various valence states. So copper, iron, uranium are the classic ones. Okay, so the change in oxidation state will govern the solubility of some metals. When that changes, we can precipitate them as commodities. As we know, fluids may be oxidized or reduced. So things like copper and uranium are transported by oxidized fluids. So the cations are transported as copper 3 plus or uranium 6 plus, and they're more soluble. And when the fluids reaches a reducing environment, the metals are reduced and precipitated out of solution. For uranium, it might be just as uranium plus, and for copper, it can be slightly more complicated, but there's a change in that conditions and the metals are no longer soluble. So iron is typically transported as ferrous iron, Fe2 plus in reduced fluids, and will precipitate when it becomes oxidized and converted to ferric iron. So it's a similar process, but of course iron is less of a key economic mineral in these systems. So you can see that this change in redox state can be an important process where we can mix fluids in different portions of the metal water table, leach out and redeposit, particularly copper and uranium. So here's just an example from a phase diagram where we have fugacity, so oxidation state going this way. As you move up, you're oxidizing. As you move down, you're reducing, versus pH. So if we think about A, where we are considering gold this time, so as gold is transported by hydrogen sulfur, acidification will lead to precipitation of gold. So if we decrease the pH, we can actually precipitate gold. You can see these concentrations of its solubility here. So much more soluble with these conditions and much less soluble at lower pH. But same can be said for oxidation. We also have a very rapid change in these contours of its solubility. So then we can also look at things like B. This is in a system where gold is transported by chlorine complexes, so distinct circumstances. Here is its solubility. Increasing pH to neutral, and reduction will cause gold to precipitate. So if we neutralize the fluid, we're going down these gradients in solubility. My apologies, I'm terrible at this. Or we can do it less so through a reduction process. So you can see the behavior of gold in these systems is dependent on the complexing agent and the redox condition. So again, we can look at things like copper in an oxidized environment with excess sulfur. Here's our, this time we're looking at EH, oxidized reduced versus pH. So we have native copper here. If we oxidize, we get cuprite and then copper oxide. At solid phases, native copper. Down here, if we can change the pH, we can also get things like cavellite, etc. Or we can move this way and we can actually dissolve copper in these complex chloride complexes. So how does this relate to ore deposits? Where do we make the money? You know, that's the important thing. So red bed copper deposits, also related to stratiform copper deposits. The key here, as the name suggests, is they form in red beds. So for those who don't know, red beds are oxidized sandstones or shales or sedimentary sequences that are interpreted to form in aeolian environments. So at the surface, in an oxidized condition, they've subsequently been buried. So they predominantly have iron oxides and mostly found in sedimentary basins like rift settings. So then we might bury these by shallow water sedimentation underneath, you know, fluvial sandstones or conglomerates. So here we have an example. We have our basement, we have a basalt, we have conglomerates, we have the red bed, arid terrestrial, and then we might have carbonates and shallow marine as we progress up the surface. So that we have initial basinal or connate fluids moving through this system. They're moving through predominantly oxidized rock types, so they're oxidized fluids where the copper is transported as copper 2 plus sulfide. And as we move further up, we intersect an area where we are reducing and we deposit out copper and sulfide. So we can get variations, but the classic examples are East Africa or Red Sea. As I say, the fluids are connate, but they're very low temperatures, 25 to 100 degrees. The hosting sediments are a variety of fluvial, dark red, brown, so there's abundant iron oxides such as hematite and goethite. When inundation of the sea occurs, marine influences result in the sediments become finer, they become shales, and they're chemically reduced, where biogenic behaviour contributes to the reduction of things like sulfur, and we also have things like graphite. So these kind of sediments become akin to estuarine environments, swamps where we have organic material. And we transition from oxidized to reduced. So there's this key change in the sedimentary environment, and this contributes to how these fluids then interact. So they move through the oxidized, deeper rocks, the red beds, things like that, and are saline, the connate fluids, and they contain copper with only limited lead, zinc, and uranium. And this relates to the lead and zinc have higher solubilities in oxidized fluids, and so they're less likely to be deposited out, but I'll get to them in a tick. And so when these interact with reduced marine sediments, they precipitate out as metal sulfides. Copper 3 plus a reductant becomes chalcopyrite. So on a smaller scale, the interface between oxidizing is very important. So you can see how these dynamics control where this will precipitate out these metalliferous minerals. So we can have a look more closely. Here's an example. We have our oxidized sandstone in this case, in a simple scenario, our reduced shales and evaporites. So they're reduced organic hydrogen. We have oxidized fluids, and as they progress, they will move closer. They intersect these reducing environment, and we end up with a progressive precipitation out of minerals as we oxidize. They change from oxidized to reduced. So we might start with hematite here, oxidizing. We will go through to chalcocite. Then we get through to chalcopyrite, bornite. Further on, we might get pyrite, galena, sphalerite, and uranium minerals. So this is the broad idea where we have an intersection of oxidizing with reducing system. As you can see here, we might have a very small vertical scale, but horizontal scale can be huge depending on the nature of these interactions and the redox states. So, 100 meters, 10 kilometers. Here's just some examples. Oxidized copper ore, both black, blue, and green in supergene cap. So we've been looking at some of these samples like malachite, azurite, classic oxidized copper ore. So you have those in your kit. Native copper also can precipitate under reduced conditions and high pH, but native copper is difficult to handle and very rarely used as an ore. Here's some malachite replacing carbonate cement in a sedimentary breccia, so it's quite spectacular, the beautiful green malachites surrounding these class sedimentary rocks. Okay, so we've seen what happens when we go oxidizing to reduced, and they're related to red bed deposits. The alternative is carbonate-hosted base metal deposits, also called Mississippi Valley type deposits. And this is slightly distinct because we're dominated by base metals, lead and zinc, and we have a distinct reaction compared to copper. So we have carbonate replacement by the sulfides in sedimentary basins. So we need carbonate material to contribute to these reactions. And they're predominantly reduced systems where we're dominated by lead, zinc transportation, and less so by copper. So fluids, again, are reasonably cold, less than 150, related to basinal dewatering. And there's no relationship to magmas. They're mostly connate fluids. And the brines leached and transport lead and zinc. And the precipitation is by mixing with sulfur sources, dilute fluids, and conductive cooling, potentially reaction with carbonate to change the pH. And the sulfides are very fine grained, potentially botryoidal, depending on the history. So the sulfides commonly replace the carbonates or the fill open spaces. The alteration tends to be very weak. We're in a low temperature system. We might get minor silicification and regional scale dolomitization. So the districts tend to be very large. But in an ideal world, you want them quite localized, and we're seeing precipitation in association to paleotopographic highs. And what that really means is the water circulation and groundwater movement is associated to ancient topographic relationships which control hydraulic heads and where the fluid moves through the basin. So the kind of sulfides we get will be sphalerite, galena, marcasite, pyrite, maybe fluorite. The sphalerite tends to be like Cara due to the absence of iron, and we can get variations based on temperature. Here's a nice example. There's a sort of zebra textured alteration of carbonate rocks with sparry dolomite in Canada. So we have aspects of potentially sphalerite intermixed with dolomite. Here's massive replacement of carbonates by sphalerite or in this case by galena, very spectacular. We have carbonate, calcite, only occurring as remnants. And just here's some more examples. Botryoidal forms, very spectacular growth sort of rings. We get these sort of jury cruciform style. This example's from Polaris in Canada. So the key here is we're actually having reduced fluids and they interact with a highly reactive carbonate source, and that's why we mainly are carrying lead and zinc and not copper. So it's distinct from our red bed system. Okay, finally, talk about uranium deposits. These are more akin to the copper systems. So they they carried well in oxidized fluids, and then when they hit a redox front, they deposit out. So we're mostly associated with circulation of groundwater. So groundwater likes to move through things like sandstones because there's lots of pore space. The deposits are strata-bound, but not necessarily concordant to bedding. So they might not have formed at the same time, and we have to have this redox change. So the reason for that is Uranus, uranium 4 plus. Iron occurs in magmatic systems where it's highly incompatible and only forms in minerals like zircon, monazite, apatite, things like that. And it readily oxidizes to uranal iron, uranium 6 plus, in meteoric water. And oxidized uranium has high solubilities in fluids, because it complexes with things like fluoride, phosphate, and carbonate under a range of pH conditions. The Uranus reduced iron is not stable. So if we change the redox stage, uranium 6 plus will be converted to Uranus iron and uranium as uraninite, so uranium oxide. So that's the key. If we can reduce the system, we can precipitate uranium as uranium oxide, uranite, also referred to as pitch blende. So here is our phase diagram. Again, we have oxidation on this axis and redox state, and we are strongly dependent on this redox condition. So oxidized systems, we have uranium oxide up here, and different types, if we might have as carbonate hosted, and there's uranium 4 plus. So as we reduce, we can stabilize uranite. So we're converting these Uranus ions to uranyl complexes. So how does this work in the sedimentary system? We can get different types. One of them is a sandstone-hosted uranium deposit. So we have these stacked lenses of sandstones with a dolomitic cement. And what happens is we mix two fluids. We have a brine mixing with a meteoric fluid. So we have oxidized and reduced fluids. So the oxidized fluids might be carrying uranium, and when they mix, they precipitate uranium and things like vanadium. And then progressively the saline aquifer migrates upwards and intersects more of the uranium-bearing groundwater, and we precipitate prominent layers. In this case, the main economic mineral is coffinite and a hydratium uranium silicate mineral. These are very low temperature systems, and the classic examples are in the Colorado Plateau and in Utah. So these are stratiform, strata-bound deposits, and they can also contain considerable vanadium. The second type is uranium roll front deposits. So these ones are strata-bound, but the mineralization is concordant to bedding. Uranium is transported in solution by fluid that flows along a sandstone aquifer and then hits a redox front. So then we get weak hydrothermal alteration, clay alteration to silicates, oxidation of iron titanium oxides, and the redox front minerals include pyrite, magnesite, goethite, and siderite. And then the ore zone is characterized by pitchblende, impure uraninite, coffinite, pyrite, organic carbon. So the deposition is related to the fluid no longer being able to oxidize the sandstone through which it passes, and the oxidation drops and destabilizes the uranium. But we can also get things like cobalt, significant source of cobalt and vanadium, as well as other metals in these systems. So here's just an example. We have a sandstone and we have an oxidation front, and we've concentrated the uranium at the boundary between this oxidized system and reduced occurrence. We can see the prominent red color here, slightly duller in this case, in this system. And how that works, this is our sandstone hosted uranium roll front deposit. We have a shale on either side. We have an aquifer with oxidized sandstone, and uranium is stable as 6+. Something happens here and we go into a reduced system. Maybe we have organics or reduced sandstone, and the uranium is immobile, transforms into a uranium ore. As we move forward, and it progressively, you'll see an alteration front as we move this way. And the idea about a roll front is potentially it migrates this way as the oxidized material oxidizes this sandstone and progressively hits a point where it can't contain uranium anymore. The final type of uranium deposits, unconformity related uranium deposits. They might also contain significant base metals, and these deposits are located at the interface between basement, commonly Proterozoic, and overlying sedimentary sequence. So we have a regional redox interface in these cases where we're going from oxidized sedimentary pile to a reduced basement, and this is where this unconformity is related to. So the fluids are oxidized as they've interacted with evaporites with high salinity, and we get, what happens is we have a basin inversion. So we compress it, we might expose components of it, and we have faults that enable fluid to migrate. And then the uranium is sourced from the basement rocks, and we have a redox front occurring in association to the unconformity between the basement and the sedimentary package. So the mineralization is massive and disseminated, potentially in breccias and shear zones, and these are classic for most Australian uranium deposits. So like Pine Creek is a world-class example. We also have Alligator River, amongst others. So here's the idea. We have basement rocks, we have a fault zone, and we might have fluid circulations where we have reduced fluids intersecting with oxidizing fluids. And then we immobilize uranium as uraninite here at the unconformity, where we mix the oxidized with the reduced material moving along a shear zone. So we have a redox front associated with this unconformity, which is the marker between the basement and the sedimentary sequence. So just to show you on a map, classic examples around the Broken Hill inlier. There's some here because we have Proterozoic on broadly Cambrian or sediments. We also have Northern Territory. We have a similar story. We have Precambrian basement and younger sedimentary sequences. So that's this unconformity related uranium deposits, a classic for Australia. So that's all from me for this week, and that's all from ore deposits. Well done, we're nearly there. We can move on to some environmental consequences, which will be a nice change. So remember that the textbook is quite a good source for more specifics on these, but the broad idea of this is to get an idea of different styles of mineralization and what's controlling them in terms of geology and tectonics. So, excellent. I'll see you next week.